Hi class, we continue our study in chapter 10 in section 10.2 talking about calculus with parametric curves, now by moving into arc length. Okay, so to set this up, we already know how to find the length L of a curve C when you're given in this form y is equal to f of x going from A to B. This is something you should have learned in calculus 2, and we know the formula for the arc length L is equal to the integral from A to B, the square root of 1 plus dy dx squared dx. Okay, but suppose that C can be described by the parametric equations x is equal to f of t and y is equal to g of t, here where our parametric parameters going from alpha to beta. Okay, well now how can we apply arc length in terms of these parametric equations? Well, this means that C is traversed once from left to right as t increases from alpha to beta. Okay, so what we're seeing here is that f of alpha is equal to A and f of beta is equal to B. Great. So putting formula 1 into formula 2 here and using the substitution rule, basically all we're doing is obtaining the following formula. Okay, and I'll skip ahead down here so you can see the arc length L is equal to the integral from alpha to beta. Okay, so this alpha to beta is where our parametric parameter goes from. So L is equal to the integral from alpha to beta, the square root of dx dt squared plus dy dt squared dt. So it's just a formula you need to follow. I will give you a tip for this. A lot of times when you go to do these problems, it's gonna involve a lot of algebra underneath the radical to get it into a method or get it into a form that you can solve with the integration methods that you know. All right, so let's just go through the formula one last time. So if a curve C is described by the parametric equations x is equal to f of t and y is equal to g of t from alpha to beta for t, where f prime and g prime are continuous on the closed interval from alpha to beta, and C is traversed exactly once as t increases from alpha to beta, then the arc length C is just that same equation. Arc length is equal to the integral of alpha to beta, the square root of dx dt squared plus dy dt squared, and you're integrating with respect to the t variable. Okay, well let's just work one example. So we're going to go back and continue with that cycloid. Okay, so let's find the length of one arch of the cycloid. Again, x is given by r times, so whatever the radius of the cycloid is, so that's just a constant. Theta minus sine theta, and y is defined as the parametric equation r times 1 minus cosine of theta. Okay, so the first thing you're going to have to do is remember that from example 3 we see that one arch is described by the parameter interval from 0 to 2 pi for theta. Awesome. So let's just see what dx d theta and dy d theta is. Here, remember, we're just, the parametric parameter is theta, not t, so wherever I see a t, I'm just replacing it with theta. Okay, so dx d theta in derivative was this, dy d theta's derivative was just this right here. Okay, so what we're going to do now, we're going to just use the formula. So the arc length is equal to the integral from 0 to 2 pi, okay, because that's what theta goes from, dx d theta squared plus dy d theta squared, the square root of that, d theta. Okay, so when you plug this stuff in, this is what you get, okay? The square root of r squared times 1 minus cosine theta, quantity squared, plus r squared sine squared theta d theta. So what you have to do, and what makes this a little tricky, is you have to evaluate this. You have to clean this up so that you can evaluate the integral. So just going through, expanding it out, and going one more step, when we fully expand it out, this is what we get. Okay, r is equal to the integral from 0 to 2 pi, the square root of 2 times 1 minus cosine theta d theta. Okay, so how are we going to integrate this, right? So you could maybe use the table of integration in your textbook, but let's talk about a way you'll approach this. So to evaluate this integral, we use the identity sine squared of x is equal to, so what we're really looking at here is we're undoing a power reduction, is equal to 1 minus cosine 2x. So the reason we're doing that, we have 1 minus cosine of theta in here. So what we're going to have to figure out is a tricky way to have it be 2 theta instead. All right, so with theta equal to 2x, all right, which gives us just the following. 1 minus cosine theta would then be equal to 2 times sine squared of theta over 2. So just figuring this one out a little bit easier, now we can plug this in. So when I go to plug this in, the square root of this now becomes this 2 times this 2 produces the 4 sine squared of theta over 2. Well, the reason that's great is the square root of 4 is 2, and square root of sine squared just gets us sine here. So now going back, we just have this integral. All right, L is equal to 2r, okay, the integral from 0 to 2 pi sine of theta over 2 d theta, which just integrates to the following. And when I plug these values in, I just get 2 radius times 2 plus 2. This ends up just being the arc length is just 8 times whatever the radius is. So the formula wasn't necessarily hard here, okay? What's really hard generally is how you clean up what's underneath the radical. And there's always going to be a method to do this, so work through it, and if you have any questions, let me know.